journey to the oldest light in the universe. You have nothing to do but rest. Let your breathing slow, let your thoughts grow quiet, and let the cosmos carry you gently to sleep. There is no hurry tonight, no task to complete, no problem to solve, no appointment waiting at the end of this journey. You are exactly where you need to be, resting, breathing, letting the world outside carry on without you for a while. If you are lying down, let your body become heavy. Let the full weight of you settle into whatever is beneath you, the mattress, the pillow, the sheets. Let them receive all of you, every kilogram, every worry, every unfinished thought from the day. You can set everything down now, the way you would place a heavy book on a nightstand, gently, deliberately, knowing it will be there in the morning, but tonight you do not need it. Let your jaw unclench, let the muscles around your eyes soften, let the small space between your eyebrows become smooth and wide, as though someone very kind has placed a warm hand there and all the tightness has melted away. Your shoulders can lower just a little, not all at once, just enough to feel the weight of the day sliding off the edges of you, down through the bed and away. Your hands can open, your fingers can uncurl, your wrists can go soft. And your breathing, you do not need to control it. Just notice it, in and out, in and out, each breath a little slower than the last, each exhale a little longer, like a wave pulling gently back from shore, leaving the sand smooth and still. The room is quiet around you. The air barely stirs. Whatever is happening beyond these walls can stay out there. Here, there is only the dark and the quiet and the story. And tonight's story is about light, the oldest light there is, light that has been traveling across the universe for 13.8 billion years, light that was born when the cosmos itself was an infant, barely 380,000 years old. This ancient light is called the cosmic microwave background, and it fills every corner of the observable universe. It is everywhere. In every direction you look, a faint, warm glow that has been bathing you since before you were born, since before the earth existed, since before the sun ignited, since before the Milky Way had finished forming. You are soaking in the oldest light in existence right now. As you lie in bed, it passes through the walls of your room, through the roof above you, through the blanket that covers you, gentle and ancient and patient beyond all imagining. And tonight we will follow that light all the way back to the moment it was born, to a time when the universe was unimaginably young, unimaginably hot, and unimaginably different from the cosmos you know today. In and out, the bed holds you, the room is dark, and the oldest light in the universe is here with you, as it has always been, as it will always be. To understand the cosmic microwave background, you first need to understand what the universe was like in the very beginning, in the first few 100,000 years after the Big Bang. The Big Bang was not an explosion in space, it was an expansion of space itself. Every point in the universe expanding away from every other point, not because things were flying apart, but because the fabric of space between them was stretching. In the very first moments after the Big Bang, the universe was extraordinarily hot and extraordinarily dense. The temperature in the first fraction of a second was trillions of degrees, hot enough that matter as you know it could not exist. No atoms, no molecules, no solid or liquid or gas, just a seething plasma of fundamental particles, quarks and gluons and electrons and photons and neutrinos, all crammed together in a space so dense and so energetic that the distinction between matter and energy was almost meaningless. As the universe expanded, it cooled. This is a simple consequence of the laws of thermodynamics. When a gas expands, it cools, and the universe was expanding very rapidly. Within the first few minutes, the temperature had dropped to about 1 billion degrees, cool enough for protons and neutrons to begin sticking together, forming the nuclei of the lightest elements: hydrogen, deuterium, helium, and a trace of lithium. This process is called Big Bang nucleosynthesis, and it took only about 20 minutes, from roughly 3 minutes after the Big Bang to about 20 minutes after. The universe was a nuclear reactor, forging the first atomic nuclei from the raw materials of the primordial plasma. After 20 minutes, the temperature had dropped too low for further nuclear reactions, and the nucleosynthesis stopped. The composition of the universe was set roughly 75% hydrogen, 25% helium, and tiny traces of deuterium and lithium. This ratio has been confirmed by observations and matches the theoretical predictions with extraordinary precision. But the universe was still far too hot for complete atoms to form. The nuclei existed, bare protons and helium nuclei, but the temperature was so high that any electron that tried to attach to a nucleus was immediately knocked free by the intense radiation. The universe was a fog, a thick, glowing fog of free electrons and bare nuclei and photons, all tangled together, all interacting constantly. The photons could not travel far before hitting an electron and bouncing off in a random direction. The universe was opaque, like looking into a thick cloud or a glass of milk. Light could not travel through it in a straight line. The room is dark around you, and you can see the darkness, which means photons are reaching your eyes from across the room without being scattered. The air is transparent. The space between you and the walls is clear. But in the early universe, there was no clear space. Everywhere was fog. Everywhere was glow. Everywhere was a thick, hot soup of matter and light bouncing off each other in every direction. In and out, the universe was a foggy nursery, warm and bright and chaotic, and the light that fills your room tonight, the cosmic microwave background, was born at the moment that fog finally cleared. That moment came 380,000 years after the Big Bang. For 380,000 years, the universe expanded and cooled. The temperature dropped steadily from billions of degrees to millions to hundreds of thousands. Each century a little cooler, each millennium a little calmer. The primordial fog slowly thinning as the universe stretched. And then, at a temperature of roughly 3,000 degrees Kelvin, about half the temperature of the surface of the sun, something extraordinary happened. The universe became cool enough for electrons to attach to nuclei and stay. Before this moment, the photons in the universe had enough energy to knock electrons free from any nucleus they tried to join, but at 3,000 degrees, the photons had been stretched and cooled by the expansion of space to the point where they no longer had sufficient energy to ionize hydrogen atoms. For the first time, electrons could settle into orbit around protons, forming complete neutral hydrogen atoms, atoms that would not be ripped apart by the surrounding radiation. This event is called recombination, although the name is slightly misleading because the electrons had never been combined with nuclei before. They were combining for the very first time, not recombining, but the name has stuck, and physicists have learned to live with it. Recombination happened everywhere in the universe at roughly the same time, not in a single instant, but over a period of roughly 100,000 years, as the temperature passed through the critical threshold. Across the cosmos, trillions upon trillions of electrons found their partners, settled into orbitals, and formed the first complete atoms in the history of the universe. And when the electrons were captured by nuclei, the fog cleared. This is the key moment, the moment that everything changed, because free electrons are excellent at scattering photons. They are the reason the universe was opaque, but neutral atoms are almost transparent to the wavelengths of light that filled the early universe. Photons could now travel in straight lines, unimpeded, free. The universe went from opaque to transparent in a cosmic eye blink, like a thick fog burning off on a summer morning. One moment you cannot see 20 meters ahead, and the next the world opens up and you can see to the horizon. The photons that had been bouncing around in the fog for 380,000 years were suddenly released, free to travel across the universe without being absorbed or scattered, and they have been traveling ever since. Those photons are the cosmic microwave background. They are the light from the moment the universe became transparent, the afterglow of the Big Bang, the oldest light in existence. They have been traveling for 13.8 billion years, and they are still arriving from every direction, filling every cubic centimeter of space with a faint, ancient glow. Your blanket is warm around you, your body is settling deeper into rest, and the photons from the birth of transparent space are passing through you right now, ancient travelers finishing a journey that began before galaxies existed. In and out, the discovery of the cosmic microwave background is one of the most beautiful stories in the history of science because it was an accident, a complete, glorious, serendipitous accident. In 1964, two young radio astronomers named Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in Holmdel, New Jersey. They were using a large horn-shaped antenna originally built for satellite communication to study radio emissions from the Milky Way. But they had a problem. No matter where they pointed the antenna, no matter what direction they looked, they detected a persistent background hiss, a low-level static that they could not get rid of. It was not coming from any particular source. It was not coming from the galaxy, or from the sun, or from any man-made interference they could identify. It was everywhere, uniform, constant, the same intensity in every direction, day and night, summer and winter, regardless of where they pointed the dish. They checked everything. They rebuilt the antenna's electronics. They sealed every joint and connection. They even climbed inside the horn and cleaned out pigeon droppings that had accumulated in the structure, thinking that perhaps the birds were the source of the noise. But the hiss remained stubborn, persistent, inexplicable. The room is quiet around you, so quiet you might hear your own breathing, or your heartbeat, or the faintest hum of the building around you. Penzias and Wilson heard something similar, a faint background noise that refused to go away, and they did not yet know that they were listening to the echo of creation itself. In and out. Meanwhile, just 60 kilometers away at Princeton University, a team of physicists led by Robert Dicke was building their own antenna, specifically designed to search for the very signal that Penzias and Wilson had accidentally found. Dicke and his colleagues knew from theoretical work dating back to the 1940s, particularly the predictions of George Gamow, Ralph Alpher, and Robert Herman, that if the Big Bang had actually happened, there should be a faint afterglow of radiation filling all of space, cooled by the expansion of the universe from its original searing temperature to just a few degrees above absolute zero. They knew what to look for. They knew roughly what temperature it should be. They knew it should be uniform in all directions. They were building the equipment to find it. And then they received a phone call from Penzias and Wilson asking if they had any idea what this mysterious background noise might be. The story goes that when Dicke hung up the phone, he turned to his colleagues and said, "Boys, we've been scooped." Penzias and Wilson had found the cosmic microwave background without knowing what it was, while Dicke's team had known what it was without being able to find it. The two groups published companion papers in 1965, Penzias and Wilson reporting the observation, and Dicke's team providing the theoretical interpretation. In 1978, Penzias and Wilson were awarded the Nobel Prize in Physics for their discovery, one of the most important discoveries in the history of cosmology, triggered by pigeons in an antenna. There is something wonderfully human about that story, the most profound observation of the century, and it was made by two people who were annoyed by a noise they could not make go away. Science does not always march forward in grand, deliberate steps. Sometimes it stumbles sideways, trips over something unexpected, and lands on a discovery that changes everything. Let your mind wander with that thought. You do not always find what you are looking for. Sometimes the most important things find you while you are busy doing something else, like resting, like drifting towards sleep. In and out. So what exactly is the cosmic microwave background, and what does it tell us? The CMB, as scientists often abbreviate it, is a nearly uniform glow of microwave radiation that fills all of space. It has a temperature of 2.725 degrees above absolute zero, which is about minus 270.4 degrees Celsius. Extraordinarily cold by human standards, but not quite absolute zero. When the CMB was first released, 380,000 years after the Big Bang, it had a temperature of about 3,000 degrees Kelvin, roughly the temperature of a red-hot piece of iron. It was visible light, the you could see with your eyes, if you had eyes, which no one did, because atoms had only just formed and biology was billions of years in the future. But over the last 13.8 billion years, the expansion of the universe has stretched the wavelength of those photons enormously. What was once visible light has been redshifted into the microwave portion of the electromagnetic spectrum, stretched by a factor of about 1,100. This stretching is not because the photons are losing energy in the usual sense. It is because the space they are traveling through is expanding, like dots drawn on a rubber band that is being stretched. The dots do not move, but the distance between them increases because the rubber itself is getting longer. The photons of the CMB are like those dots. They are not slowing down. They are still traveling at the speed of light, but the space between them and the space they are traveling through has been stretching for 13.8 billion years, and that stretching has increased their wavelength from visible light to microwaves. The CMB has a very specific kind of spectrum called a blackbody spectrum. This is the spectrum of radiation emitted by an object in thermal equilibrium, and it has a characteristic shape that depends only on the temperature of the object. The CMB has the most perfect blackbody spectrum ever measured. When the COBE satellite measured it in 1990, the data points fell so precisely on the theoretical blackbody curve that the error bars were smaller than the width of the line used to draw the curve. It was described at the time as the most perfect blackbody spectrum in nature. This perfection tells us something important. It tells us that the early universe was in extraordinarily precise thermal equilibrium. Every part of it was at the same temperature. Every direction yielded the same radiation, to an accuracy of better than 1 part in 100,000. The universe 380,000 years after the Big Bang was one of the smoothest, most uniform, most thermally balanced systems that has ever existed. The bed is warm, the room is still, your body is in its own kind of thermal equilibrium with the blanket and the air warm and balanced and at rest, and the universe was once in a similar state, warm and balanced and smooth, before gravity began its slow work of pulling matter together into stars and galaxies and planets and people. In and out. But the cosmic microwave background is not perfectly uniform, and the tiny imperfections it does contain are among the most important measurements in all of cosmology. When Penzias and Wilson first detected the CMB, their instruments were not sensitive enough to detect any variation in temperature from one direction to another. It looked the same everywhere, uniform and featureless. But physicists knew there had to be variations, however small, because if the early universe had been perfectly smooth, perfectly uniform in every way, then gravity would have had nothing to work with. No region would have been denser than any other, and there would have been no reason for matter to clump together into galaxies and stars and planets. The universe we see today, with its galaxies and clusters and vast empty voids, is anything but uniform. So the seeds of that non-uniformity must have been planted very early, perhaps in the first tiny fraction of a second after the Big Bang, and those seeds should be visible in the CMB as tiny variations in temperature from one spot to another. Finding those variations became one of the great quests of observational cosmology. The first satellite dedicated to studying the CMB in detail was COBE, the Cosmic Background Explorer, launched by NASA in 1989. COBE carried an instrument called the Differential Microwave Radiometer, which could measure temperature differences across the sky with a sensitivity of about 1 part in 100,000. And in 1992, the COBE team announced their results. They had found the variations, tiny ripples in the temperature of the CMB, just 30 millionths of a degree warmer in some spots and 30 millionths of a degree cooler in others. These temperature variations are called anisotropies, and they represent the seeds of all the structure in the universe. The slightly warmer spots correspond to regions where the primordial plasma was slightly denser, and those denser regions had slightly more gravity, which attracted more matter, which grew denser still, and eventually, over billions of years, collapsed to form the galaxies and clusters of galaxies we see today. The famous oval map of the CMB, the one you may have seen in textbooks or online, with its patches of blue and red and yellow on a cosmic oval, that map shows these temperature fluctuations magnified and color-coded so that human eyes can see differences that are far too small to detect with any human sense. When the lead scientist on the COBE project, George Smoot, presented the results to the world, he described the CMB anisotropies as looking at the face of God. It was a dramatic statement, perhaps overly dramatic, but it captured something real, the sense of awe that comes from seeing the universe as it was at the very beginning of its journey from simplicity to complexity. The pillow is soft beneath your head, your muscles have let go of their holding, and the light from 380,000 years after the Big Bang carries within it the blueprint for everything, the pattern of density variations that would one day become the Milky Way, the Sun, the Earth, and you. In and out. The discovery was so important that Smoot and his colleague John Mather were awarded the Nobel Prize in Physics in 2006 for their work on COBE. But COBE was just the beginning. Its resolution was limited. It could see the broad features of the CMB anisotropies, but not the fine details. It was like looking at a landscape through frosted glass. You could make out the general shapes, but the sharpness was missing. The next generation of CMB observation would bring that sharpness, and with it, a revolution in our understanding of the universe. In 2001, NASA launched a satellite called WMAP, the Wilkinson Microwave Anisotropy Probe, named after David Wilkinson, one of the original Princeton physicists who had been trying to detect the CMB when Penzias and Wilson scooped them in 1964. WMAP orbited at a point called the second Lagrange point, or L2, about 1.5 million kilometers from Earth, in the opposite direction from the Sun, far enough from the Earth and Moon to avoid their heat and radio interference, a quiet cold perch from which to listen to the oldest light in the universe. Over over 9 years of observations, WMAP produced a map of the CMB with 35 times the resolution of COBE, revealing fine details that had been invisible before. The broad brushstrokes of COBE became a detailed portrait, showing the precise pattern of hot and cold spots across the entire sky. And then came Planck. The Planck satellite was launched by the European Space Agency in 2009, and it observed the CMB with even greater precision than WMAP at multiple frequencies, with sensitivity to temperature differences of just a few millionths of a degree. The Planck map of the CMB is the most detailed image of the early universe ever produced. It shows the temperature of the cosmic microwave background across the entire sky with a resolution fine enough to reveal structures that were only tens of millions of light years across at the time the light was emitted. When you look at the Planck CMB map, you are seeing the universe as it was 380,000 years after the Big Bang, a time when it was roughly 1,000 times smaller than it is today. A time when the temperature everywhere was about 3,000 degrees. A time when the first atoms were just forming and the first light was just being released. It is a baby picture of the universe, the earliest image we can ever take of the cosmos, because before recombination, the universe was opaque. We cannot see further back than this moment, not with light. The CMB is a wall of light, the last scattering surface, the boundary beyond which we cannot see, because the universe itself was a fog of hot plasma that scattered every photon in every direction. Whatever happened before this moment in the first 380,000 years is hidden behind the fog. We can infer what happened using physics and mathematics, but we cannot see it directly. The CMB is the earliest snapshot, the oldest photograph, the very first image in the universe's family album. The room is dark and quiet, your eyelids are heavy, and the oldest photograph in the universe is here with you, painted across the sky in every direction, a portrait of the cosmos as an infant, still warm from the Big Bang, not yet aware of the galaxies and stars and planets and people it would one day become. In and out. Let us now think about what was happening in the universe in the time between the Big Bang and recombination, those first 380,000 years that are hidden behind the wall of the CMB. The first second after the Big Bang was the most eventful second in the history of the universe. More happened in that single second than in the billions of years that followed. In the first tiny fraction of a second, an interval so short that human language lacks words to describe it, the universe may have undergone a period of extraordinarily rapid expansion called inflation. Inflation is the idea that the universe expanded by a factor of at least 10 to the power of 26, 100 trillion in a time of roughly 10 to the power of minus 36 seconds, a trillionth of a trillionth of a trillionth of a second. During inflation, the universe grew from something smaller than a proton to something larger than the observable universe today, in less time than it takes a photon to cross the width of an atom. This idea sounds outrageous, and perhaps it is, but it solves several deep puzzles about the universe that have no other satisfactory explanation. The first puzzle is the horizon problem. The CMB looks the same in every direction to a precision of 1 part in 100,000, but regions on opposite sides of the sky are so far apart that light has not had time to travel between them since the Big Bang. How can they be at the same temperature if they have never been in contact? Inflation solves this by proposing that all the regions we can see today were once in close contact, squeezed together in a tiny volume before inflation blew them apart. They reached the same temperature when they were close together, and then inflation stretched them to enormous distances, preserving their uniformity. The second puzzle is the flatness problem. The universe is flat or extremely close to flat, but for the universe to be flat today, it had to be flat to an almost absurd degree of precision at the very beginning. Any tiny deviation from flatness would have been amplified by the expansion of the universe over billions of years. Inflation solves this by stretching space so enormously that any initial curvature was smoothed out, just as the surface of a balloon appears flat when you zoom in close enough. Inflation stretched the universe so much that any curvature became undetectable. And the third puzzle, perhaps the most important one, is where the temperature fluctuations in the CMB came from in the first place. Inflation provides an answer that is both strange and beautiful. The fluctuations originated as quantum fluctuations, tiny random variations in the energy density of the vacuum, the same kind of quantum jittering that underlies the Heisenberg uncertainty principle. In normal circumstances, quantum fluctuations are unimaginably small. They exist on scales far smaller than an atom, and they appear and disappear so quickly that they have no lasting effect. But during inflation, the expansion of space was so rapid that these tiny quantum fluctuations were stretched to cosmic scales before they could disappear. They were frozen into the fabric of space itself, locked in as permanent variations in density that would later be amplified by gravity into galaxies and clusters and the large-scale structure of the universe. This is one of the most extraordinary ideas in all of physics. The galaxies you see in the night sky, the Milky Way, the Andromeda Galaxy, every galaxy in the observable universe may trace their origin back to quantum fluctuations that occurred in the first trillionth of a trillionth of a trillionth of a second after the Big Bang. The largest structures in the universe may have grown from the smallest possible seeds. The cosmic and the quantum are connected by inflation, by time, and by the patient work of gravity over 13.8 billion years. Your body is quiet and still. Your thoughts are slowing, and the universe began from quantum whispers so small that they existed on scales smaller than an atom and grew them into everything. In and out. After inflation ended, the universe continued to expand and cool, but at a much slower rate. The extreme energies of the inflationary period decayed into a hot soup of particles and radiation, and the universe entered the radiation-dominated era. For the first 47,000 years or so, radiation dominated the energy content of the universe. Photons were the most important constituent, carrying more energy per unit volume than the matter they interacted with. During this era, the expansion rate of the universe was determined primarily by the energy density of radiation, and the temperature dropped proportionally to the inverse of the square root of the age of the universe. A precise mathematical relationship that physicists can calculate with extraordinary accuracy. Then, roughly 47,000 years after the Big Bang, the density of matter overtook the density of radiation, and the universe entered the matter-dominated era. This transition did not happen suddenly. It was a gradual crossover, but it changed the way the universe expanded, and it affected the growth of the density fluctuations that would later form galaxies. In the radiation-dominated era, the pressure of the photons prevented matter from clumping together on small scales. The sound waves we discussed earlier kept the plasma stirred up, preventing gravitational collapse. But dark matter, which does not interact with photons, was free to clump even during the radiation era. Dark matter particles fell toward the centers of the density fluctuations, slowly building up concentrations of invisible mass, scaffolding that would later attract ordinary matter once the photons released their grip. This is why dark matter is so important to the story of the CMB. Without dark matter, the density fluctuations in the CMB would have been too small to grow into galaxies in the time available. The dark matter provided the extra gravitational pull needed to amplify the initial perturbations into the structures we see today. The blanket is warm around you. You are surrounded by invisible warmth, held by invisible forces, and the universe was shaped by invisible dark matter, providing the gravitational framework that turned tiny ripples in the CMB into the galaxies and clusters that light up the sky. In and out, let us now explore what the CMB has taught us about the universe, because the information encoded in those ancient photons is breathtaking in its richness and precision. The pattern of hot and cold spots in the CMB is not random. It has a very specific statistical structure that encodes information about the composition, the geometry, and the history of the universe. One of the most important things the CMB has revealed is the age of the universe. By analyzing the pattern of temperature fluctuations and fitting them to theoretical models, cosmologists have determined that the universe is 13.797 billion years old, give or take about 20 million years. 20 million years of uncertainty on 13.8 billion years. That is a precision of better than 0.2%. It is like measuring the distance from Sydney to London and being uncertain by only a few kilometers. The CMB has also revealed the composition of the universe, and the answer is one of the most surprising results in modern science. Ordinary matter, the kind you are made of, the kind that makes up stars and planets and gas clouds and everything you can see and touch, makes up only about 5% of the total energy content of the universe. Dark matter, the invisible substance that does not emit or absorb light but exerts gravitational influence on everything around it, makes up about 27%. And the remaining 68% is dark energy, a mysterious force that is causing the expansion of the universe to accelerate. 5% visible matter, 27% dark matter, 68% dark energy. These numbers come primarily from the CMB, refined by other observations, but fundamentally rooted in the pattern of ancient light that fills the sky. It is a humbling result. Everything you have ever seen or touched or known, every star in every galaxy, every planet, every grain of sand, every atom in your body, all of it together makes up only 1/20th of the total content of the universe. The rest is dark and mysterious and still poorly understood. You are a rare thing, made of rare stuff, in a universe dominated by forces and substances you cannot directly perceive, and yet here you are, thinking about it, lying in a warm bed, breathing, resting. In and out. The CMB has also told us about the geometry of the universe, specifically whether the universe is flat, curved like a sphere, or curved like a saddle. In a flat universe, parallel lines stay parallel forever. The angles of a triangle add up to exactly 180 degrees, and space stretches on in all directions without curving back on itself. In a positively curved universe, like the surface of a sphere, parallel lines eventually converge. The angles of a triangle add up to more than 180 degrees, and if you traveled far enough in a straight line, you would eventually return to your starting point. In a negatively curved universe, like the surface of a saddle, parallel lines diverge. The angles of a triangle add up to less than 180 degrees, and space opens outward in all directions. The CMB tells us which of these possibilities is correct because the geometry of the universe affects the apparent size of the temperature fluctuations. In a positively curved universe, the hot and cold spots would appear larger than expected. In a negatively curved universe, they would appear smaller. In a flat universe, they would appear at exactly the size predicted by theory. The result, confirmed by WMAP and Planck with extraordinary precision, is that the universe is flat or very, very close to flat, to within 1%. Space is flat. Parallel lines remain parallel. Triangles have angles that add up to 180 degrees. The geometry you learned in school applies to the entire cosmos, at least on the largest scales. There is something oddly comforting about that. The universe is not curved in some strange, unfamiliar way. It is flat, straightforward, the geometry of a tabletop extended to the size of the observable universe. Simple and vast and honest. The bed beneath you is flat, the floor is flat, the horizon is flat, and the universe itself is flat, at least as far as we can measure. In and out. One of the most remarkable features encoded in the CMB is a phenomenon called baryon acoustic oscillations, and despite the intimidating name, the idea behind it is beautiful and surprisingly simple. In the early universe, before recombination, the primordial plasma was filled with sound waves. Not sound as you hear it, not vibrations in air, but pressure waves traveling through the hot, dense plasma at roughly half the speed of light, waves caused by the competition between two forces. Gravity pulled matter inward toward the densest regions, compressing it, heating it, but the increased pressure of the compressed gas pushed back outward, resisting the compression, creating a bounce, which sent a pressure wave rippling outward through the plasma. These waves were the sound of the early universe, the cosmic equivalent of sound, compression waves propagating through a medium just as sound propagates through air. The universe was ringing like a bell that had been struck, vibrating with standing waves at specific frequencies determined by the size and density and temperature of the plasma. When recombination happened, when the fog cleared and the photons were released, these sound waves were frozen in place. The pressure that had been sustaining the waves disappeared because the photons decoupled from the matter, and the pattern of compression and rarefaction was locked into the distribution of matter. The CMB carries the imprint of these frozen sound waves. The pattern of hot and cold spots is not random. It has a characteristic scale, a preferred size that corresponds to the distance a sound wave could travel in the 380,000 years between the Big Bang and recombination. This distance is about 450,000 light-years at the time of recombination, and it shows up in the CMB as a preferred angular size of about 1 degree on the sky, roughly twice the apparent diameter of the full moon. The hot and cold spots in the CMB tend to be about 1 degree across, not because of coincidence, but because that was the size of the largest sound wave that could fit in the universe at the time the music stopped. Your breathing is a kind of sound wave too, a pressure wave in the air, moving in and out of your lungs, and the rhythm of your breathing tonight has the same fundamental physics as the acoustic oscillations that shaped the CMB. Compression and expansion, pressure and release, in and out, in and out. The frozen sound waves did not just stay in the CMB, they also left their mark on the distribution of matter in the universe. The pressure waves that were propagating through the plasma at the time of recombination had pushed ordinary matter outward from the densest regions, creating shells of slightly enhanced density around each initial overdensity. After recombination, these shells stopped expanding, and over billions of years, gravity caused galaxies to form preferentially at the locations of these density enhancements, both at the original centers and on the shells. The result is that galaxies today are slightly more likely to be found separated by a specific distance, about 490 million light-years in today's expanded universe, than at any other distance. This is the Baryon acoustic oscillation scale, and it has been measured in surveys of millions of galaxies. It is a cosmic ruler, a standard measuring stick built into the very fabric of the universe by sound waves that propagated through the primordial plasma 13.8 billion years ago, and it allows cosmologists to measure the expansion rate of the universe with extraordinary precision. The room holds you. The bed holds you, and the universe holds within itself a ruler made of ancient sound, a measuring stick woven into the pattern of galaxies by oscillations that rang through the cosmos before any star had formed. In and out, let us return now to the moment of recombination and experience it more slowly, more gently, the way a dreamer might replay a memory and notice details they missed the first time. The universe at 380,000 years old was a remarkable place. It was still very young in terms of the universe's current age of 13.8 billion years. 380,000 years is like the first 7 hours of a person's life, an infant barely born, still warm from the process of creation. The temperature everywhere was about 3,000 degrees Kelvin, roughly the temperature of a candle flame, warm enough to glow with a deep red-orange light. The entire universe glowed. Every direction was filled with this warm light. There was no darkness anywhere. The concept of darkness did not yet exist because light was everywhere, trapped in the fog, bouncing between free electrons, filling every cubic centimeter of space with a dense, warm glow. And then, over a period of roughly 100,000 years, the electrons began to find their partners. One by one, across the universe, electrons settled into orbit around protons, forming hydrogen atoms, and around helium nuclei, forming helium atoms. Each capture removed one more scattering target from the path of the photons. Each atom that formed made the universe a little more transparent, a little clearer. The fog thinned, not all at once, but gradually, like morning mist burning off as the sun climbs higher. The universe grew clearer and clearer, the photons traveling farther and farther between scattering events, until finally, the last electrons were captured, and the universe became fully transparent. And the light that had been trapped for 380,000 years was free. Imagine being a photon at that moment. You have been bouncing around in a thick, hot fog since the universe was born, never able to travel more than a short distance before hitting an electron and being scattered in a random direction. And then, suddenly, the fog lifts. The electrons disappear into atoms, and you can see all the way to the edge of the universe. You fly forward in a straight line for the first time in your existence, and you keep flying for 13.8 billion years across an expanding universe, your wavelength stretching, your energy fading, until one night you pass through the wall of a room on a small planet orbiting an ordinary star, and you arrive, ancient and faint and patient, having finally completed the longest journey any photon can make. The room is dark and still, and that photon is here, right now. It has been traveling since the universe was 380,000 years old, and it has arrived at this room, at this moment, at you. In and out, the oldest light in the universe is keeping you company tonight. After recombination, the universe entered a period that astronomers have poetically named the Dark Ages. The CMB photons had been released, but there were no stars yet, no galaxies, no sources of new light. The universe was filled with neutral hydrogen gas, slowly cooling, slowly condensing under the influence of gravity and dark matter, but not yet hot enough or dense enough to ignite the first stars. The Dark Ages lasted for roughly 100 to 200 million years, and during this time, the universe was truly dark. The only light was the fading afterglow of the CMB, growing dimmer and redder as its photons were stretched by the expanding space. If you could have been present during the Dark Ages, floating in the void, you would have seen nothing. Absolute blackness in every direction. of the CMB, invisible to human eyes, and a vast, quiet ocean of hydrogen gas, slowly, slowly falling inward toward the densest regions. It is perhaps the most peaceful era in the history of the universe, a time of pure potential, matter gathering but not yet shining, structure forming but not yet visible, the universe holding its breath before the first star would break the silence. The Dark Ages ended when the first stars ignited, somewhere between 100 and 400 million years after the Big Bang. These first stars were unlike any star in the modern universe. They were made entirely of hydrogen and helium, with no heavy elements at all, because no star had yet lived and died to produce them. The first stars were massive, perhaps hundreds of times the mass of our Sun, and they burned with extraordinary brightness and ferocity. Their ultraviolet light ionized the hydrogen gas around them, splitting atoms apart, recreating the plasma conditions that had existed before recombination, but this time in bubbles around each star rather than throughout the entire universe. This process is called reionization, and it gradually filled the universe with ionized hydrogen again as more and more stars formed and their radiation bubbles expanded and merged. By about 1 billion years after the Big Bang, the reionization was complete and the universe had transitioned from its dark neutral state to the bright ionized state we see today. The CMB photons passing through this reionized gas were slightly affected. A few % of them were scattered by the newly freed electrons, smearing the CMB pattern very slightly on the smallest scales. This effect has been measured by Planck, and it provides information about when reionization occurred and how long it took. Everything is connected. The CMB carries information not only about the moment it was born, but about everything that happened to it during its 13.8 billion year journey. Every interaction, every scattering, every stretch of its wavelength is recorded in the statistics of the ancient light. Your eyelids are heavy, your body is warm and still, and the CMB is like a cosmic journal, a record of every era the universe has passed through, written in the language of photon wavelengths and temperature fluctuations. A diary that has been traveling since the universe was an infant. In and out. Let us now think about something that makes the CMB even more remarkable, something that connects the quantum world to the cosmic world in a way that is almost too beautiful to be true. The temperature fluctuations in the CMB are not just random noise. They have a very specific statistical pattern called a power spectrum, which shows how much variation exists at different angular scales. If you think of the CMB map as a kind of music, the power spectrum is like breaking that music down into its component notes, showing which frequencies are loud and which are quiet. And the CMB power spectrum has peaks, specific angular scales where the fluctuations are stronger than at others. These peaks correspond to the harmonics of the sound waves that were ringing through the primordial plasma. The first peak, the tallest one, occurs at an angular scale of about 1 degree. This corresponds to the fundamental mode of the cosmic sound, the largest wave that could complete one full compression before recombination froze the pattern in place. The second peak corresponds to a wave that completed one full compression and one full rarefaction, like the first overtone of a musical instrument. The third peak corresponds to a wave that completed 1.5 cycles, the second overtone. And so on, peak after peak, each one corresponding to a higher harmonic of the cosmic sound. The heights of these peaks, their positions, their relative sizes, all carry information about the universe. The ratio of the first peak to the second peak tells us the ratio of ordinary matter to total matter. The position of the first peak tells us the geometry of space. The spacing between the peaks tells us the density of ordinary matter with extraordinary precision. The CMB power spectrum is one of the most information-rich measurements in all of science. A single curve showing a few peaks and troughs encodes the age of the universe, its geometry, its composition, the amount of dark matter, the amount of dark energy, the expansion rate, the density of ordinary matter, and the initial conditions from which all structure grew, all from the pattern of hot and cold spots in the afterglow of the Big Bang. The universe wrote its autobiography in light 13.8 billion years ago, and we have learned to read it. The pillow holds your head, the room is quiet, and the universe has been whispering its secrets in the language of ancient photons for as long as it has existed. Tonight, you can hear the echoes, not with your ears, but with your imagination, which is the best instrument any human has ever built. In and out. There's another signal hidden within the CMB that scientists are searching for, a signal that would provide direct evidence of inflation and potentially revolutionize our understanding of the very first moments of the universe. This signal is called the B-mode polarization signal from primordial gravitational waves. The CMB light is polarized, which means the electromagnetic waves that make it up are not vibrating randomly in all directions. They have a preferred orientation. This polarization was imprinted during recombination, when photons scattered off electrons one final time before being released. There are two types of polarization patterns in the CMB, E modes and B modes, named by analogy with electric and magnetic field patterns. E modes have been detected and measured with great precision. They are produced by the same density fluctuations that produce the temperature anisotropies, and they confirm and refine the same cosmological parameters. B modes are more elusive. They can be produced by two things. One is the gravitational lensing of CMB photons as they pass through the large-scale structure of the universe, bending their paths and distorting their polarization patterns. This type of B mode has been detected and is well understood. The other source of B modes is far more exciting. Primordial gravitational waves, ripples in space-time itself, produced during inflation. These gravitational waves would have stretched and squeezed the primordial plasma, imprinting a very specific pattern of B-mode polarization on the CMB that no other process can mimic. detecting this primordial B-mode signal would be a direct confirmation that inflation happened, and it would provide information about the energy scale at which inflation occurred, opening a window into physics at energies far beyond what any particle accelerator could ever reach. So far, the primordial B-mode signal has not been definitively detected. Several experiments have searched for it, including the BICEP and South Pole telescope collaborations, but the signal is expected to be extraordinarily faint, buried beneath foreground contamination from dust in our own galaxy. In 2014, the BICEP 2 team announced that they had found the signal, generating enormous excitement in the physics community, but further analysis revealed that the signal they detected was likely produced by polarized dust emission from the Milky Way rather than by primordial gravitational waves. The claim was withdrawn, and the search continues. This is science in action, messy, uncertain, full of false starts and corrections, but always moving forward, always refining, always getting closer to the truth. The search for primordial B-modes is one of the most important ongoing experiments in cosmology. New telescopes are being built at the South Pole, in the Atacama Desert in Chile, and in space with greater sensitivity than ever before, each one designed to peel back one more layer of the cosmic story, to listen a little more carefully to the whisper of the oldest light. The room is dark and quiet, and scientists somewhere on Earth are pointing their instruments at the sky right now, listening for a signal that was produced a trillionth of a trillionth of a trillionth of a second after the beginning of time, a signal that would tell us how the universe began. In and out. Let us think now about the CMB in a more personal way, because this ancient light is not just a scientific curiosity, it is something you encounter every day, whether you know it or not. If you have ever seen static on an old television set, the snowy flickering pattern on a screen tuned to no channel, then you have seen the cosmic microwave background. About 1% of the static on an analog television is caused by CMB photons hitting the antenna, ancient light from the birth of the universe being picked up by your TV set and displayed as random noise on the screen. It is a strange and wonderful thought that among the flickering grey dots on a television screen, some of them are messages from 13.8 billion years ago, mixed in with the interference from local radio stations and electrical appliances and the thermal noise of the antenna itself. The oldest light in the universe arriving at your living room and being displayed as static. The CMB is also responsible for about 1% of the noise in any microwave receiver, including the ones used in mobile phone towers and satellite communication systems. The cosmic microwave background is a faint but persistent source of background noise in all radio communications on Earth. Every phone call you have ever made, every text message, every streaming video has been accompanied by the faintest whisper of the CMB, the oldest light in the universe, adding its voice to the conversation. Uninvited, but always present. The room is quiet, but it is not truly empty of radiation. The CMB fills it, along with infrared radiation from the walls and ceiling and floor and your own body, and radio waves from distant transmitters. and the faint glow of any screens that might be on. A symphony of electromagnetic radiation at many frequencies, all of it invisible, all of it passing through you and around you and through the walls. In and out. The CMB has a temperature of 2.725 degrees above absolute zero. This means the universe has a temperature. The empty space between galaxies is not at 0 degrees. It has a minimum temperature set by the CMB. No object in the universe can cool below this temperature without actively pumping heat away from itself, because the CMB photons are constantly arriving from every direction, depositing their tiny amounts of energy on everything they encounter. Even in the coldest voids between galaxy clusters, where there are almost no atoms for millions of light years, the temperature is 2.725 degrees Kelvin, because the CMB fills even those voids evenly, uniformly, patiently. The universe has a thermostat, and it is set by the afterglow of the Big Bang. This temperature is slowly dropping as the universe continues to expand. The CMB photons continue to be stretched, losing energy, growing cooler. In another 13.8 billion years, the temperature will have dropped to about half its current value, and in the far, far future, trillions of years from now, the CMB will be so faint and so cold that it will be essentially undetectable, a ghostly memory of the hot, bright universe that once existed. But tonight, it is still here, still warm enough to be detected by radio telescopes and satellite instruments, still carrying its ancient information across the sky, still bathing everything in a faint, gentle glow that has been traveling since the universe was young. In and out. Let us now think about one of the most intriguing anomalies in the CMB, something that has puzzled cosmologists since it was first noticed in the WMAP data and confirmed by Planck. The CMB is almost perfectly uniform, but the almost is important. When you remove the expected temperature fluctuations, the ones predicted by the standard cosmological model, there remain a few features that are not easily explained. One of these is called the cold spot, a region in the southern sky in the direction of the constellation Eridanus that is slightly colder than the surrounding CMB by about 70 millionths of a degree. It is also larger than typical CMB fluctuations, spanning about 5 degrees on the sky, roughly 10 times the apparent diameter of the full moon. The cold spot is unusual because it is statistically unlikely, but not impossible, to arise from the random fluctuations predicted by the standard model. It sits at the edge of what the theory allows, a 3 sigma outlier in statistical language. Several explanations have been proposed. It might be a statistical fluke, an unlikely but not impossible random fluctuation, or it might be caused by a supervoid, an enormous region of space with very few galaxies, that the CMB photons passed through on their way to us, losing a tiny amount of energy as they traversed the void. Some more speculative proposals have suggested that the cold spot might be evidence of something exotic, a collision between our universe and another universe, a relic of a pre-Big Bang epoch, a sign of some new physics beyond the standard model. Most cosmologists favor the less dramatic explanations, but the cold spot remains an active area of research, a small mystery embedded in the largest thing we can see. There is also a slight asymmetry in the CMB. One hemisphere of the sky has slightly larger fluctuations than the other. This hemispheric asymmetry is small, but it has been consistently observed by both WMAP and Planck, and it is not predicted by the simplest versions of inflation. These anomalies may turn out to be nothing, statistical flukes or subtle instrumental effects, or they may be clues to something deeper, signs of physics beyond our current understanding, hints that the universe is stranger than our theories have yet grasped. The universe is not obligated to be simple or to match our expectations. It is under no requirement to fit neatly into our models. It is free to surprise us, and it frequently does. Your thoughts are drifting now, loosening, the way the edges of a mystery loosen when you stop trying to solve it and simply let it be. Some questions are meant to be lived with rather than answered, held gently rather than gripped tightly, and the anomalies of the CMB are like that, beautiful unsolved puzzles at the boundary of human knowledge. In and out, let us spend a few final moments with the dipole anisotropy, because it tells us something extraordinary about our motion through the cosmos. When Penzias and Wilson first measured the CMB, they found it to be uniform in all directions, but later, more precise measurements revealed that the CMB is very slightly warmer in one direction and very slightly cooler in the opposite direction, a pattern called a dipole. The temperature difference is about 3.4 millidegrees, roughly 0.1% of the average CMB temperature. The warmest direction is toward the constellation Leo, and the coolest direction is toward the constellation Aquarius. This dipole is not a feature of the CMB itself. It is caused by our motion, the Earth, the Sun, the Milky Way, our entire local group of galaxies are all moving through space relative to the CMB at a speed of roughly 630 kilometers per second. In the direction we are moving toward, the CMB photons are slightly blue-shifted, compressed, arriving with slightly more energy and therefore appearing slightly warmer. In the opposite direction, they are slightly red-shifted, stretched, arriving with slightly less energy and appearing slightly cooler. This is the same Doppler effect that makes an ambulance siren sound higher-pitched as it approaches you and lower-pitched as it moves away. Applied to light, it shifts the wavelength and therefore the apparent temperature. The CMB dipole tells us that we are hurtling through the cosmos at more than 600 kilometers per second, about 2.3 million kilometers per hour, pulled by the gravitational attraction of enormous concentrations of mass beyond our galaxy, structures called the Great Attractor and the Shapley Supercluster. You are lying in bed, feeling perfectly still, and yet you are moving through the universe at 630 kilometers per second. Your body, your bed, your house, the entire Earth, all of it rushing through space at a speed that would carry you from Sydney to London in about 30 seconds. And you feel nothing because everything around you is moving at the same speed, and motion is always relative. In your frame of reference, you are still in the frame of reference of the CMB. You are a projectile hurtling through ancient light at more than 500,000 meters per second. Stillness and velocity coexisting the way wakefulness and sleep coexist at the boundary of consciousness, the way simplicity and complexity coexist in the pattern of the CMB, the way the ancient and the present coexist in the photons passing through your body. In and out. The CMB is a cosmic speedometer telling us how fast we are moving and in which direction relative to the frame of reference defined by the afterglow of the Big Bang, the closest thing the universe has to an absolute frame of rest. When the dipole is subtracted from the CMB map, the remaining signal is the true primordial pattern, the temperature fluctuations that encode the seeds of cosmic structure, the baby picture we have been describing. Every measurement of the CMB must first account for our motion through it, peeling away the dipole to reveal the ancient pattern beneath, like brushing dust off an old painting to reveal the original brush strokes. The universe reveals itself in layers, and each layer must be carefully removed to see the one beneath: our motion, the emission from our galaxy, the emission from other galaxies. All of it must be subtracted before the primordial signal emerges, clean and clear and ancient. It is painstaking work, patient work, the kind of work that takes years and teams of brilliant people and instruments of extraordinary sensitivity. But the reward is worth the effort, because beneath all the layers, beneath our motion and our galaxy's emission and the foreground contamination, lies the oldest signal in the universe, the afterglow of the beginning, the pattern from which everything grew. And that pattern is beautiful, not beautiful in the way a sunset is beautiful, or a flower or a face, but beautiful in the way truth is beautiful, in the way simplicity giving rise to complexity is beautiful, in the way a single set of initial conditions can produce an entire universe of stars and galaxies and planets and life and consciousness and wonder. The room is quiet, your breathing is slow, your body is still and warm and heavy with rest, and the afterglow shines on. In and out. In and out. Let us pause now and rest with the story for a moment, not adding anything new, just breathing and being. Feel the weight of your body on the bed, the broad surface of your back pressing gently into the mattress, your heels heavy against the sheets, your arms resting at your sides, your fingers loosely curled. You're a warm body in a cool room, radiating heat into the air around you, just as the early universe radiated heat into the expanding void. Your body is a tiny source of thermal radiation, emitting infrared photons from your skin, photons that carry the warmth of your metabolism, the energy of the food you ate today, which was itself energy from the sun, which was energy from nuclear fusion, which was energy from the gravitational collapse of a molecular cloud, which was energy from the Big Bang itself. The energy that keeps you warm tonight was born 13.8 billion years ago. It has been transformed many times, from the radiation of the early universe to the kinetic energy of matter, to the nuclear energy of stars, to the chemical energy of food, to the thermal energy of your body. But it was never created and never destroyed, only transformed, passed along, shared. The cosmic microwave background is the same energy, still traveling, still being transformed, still being shared with every object it encounters. You and the CMB are cousins, born from the same Big Bang, made of the same energy, traveling through the same universe, arriving at the same moment. In and out. Let us now think about what the universe looks like from the perspective of the CMB photons themselves. A photon travels at the speed of light, always, without exception, in the photon's own reference frame. If such a thing can be said to exist, no time passes during its journey. A photon emitted at the moment of recombination and arriving at your eye tonight has experienced no elapsed time at all. For the photon, the moment of emission and the moment of absorption are the same moment. This is one of the strange consequences of Einstein's theory of special relativity. Time slows down as you approach the speed of light, and at the speed of light itself, time stops completely. From the photon's perspective, the entire 13.8 billion year history of the universe happened in an instant. The formation of galaxies, the birth of stars, the evolution of life on Earth, the building of civilizations, your birth, your growth, this night, this room, this breath, all of it happened simultaneously in the zero-duration experience of a photon that left the last scattering surface and arrived at your body without any time passing in between. There is something dreamlike about that. Events that appear sequential from your perspective are simultaneous from the photon's perspective. Past and present collapsed into a single moment, distance and duration compressed to nothing. Dreams work a little like that too. In dreams, time is flexible. Events from different periods of your life can coexist. Places you have never been can feel familiar. The boundaries between then and now become soft and permeable. Perhaps you are approaching that state now. The boundaries between wakefulness and sleep growing softer, the rigid structure of conscious thought giving way to something more fluid, more dreamlike, more like the timeless journey of a photon. In and out, let time become soft, let the edges blur. You are safe here, in this room, in this bed, and the ancient light is with you. Let us return to the surface of last scattering, that spherical wall of light that surrounds us in every direction, and think about what it means for our view of the universe. When you look at the CMB, you are looking at a sphere of light centered on you. In every direction you look, you see the same thing. The surface of the universe at the age of 380,000 years. The moment when the fog cleared and light was free to travel. This sphere is called the surface of last scattering, and it is the farthest thing we can see in the universe, not in terms of distance today, but in terms of look-back time. We are seeing light from 13.8 billion years ago, and nothing visible can be older than that. The surface of last scattering is like a cosmic horizon, a boundary beyond which we cannot see, not because there is nothing there, but because the universe was opaque before that moment. The wall is not made of something solid. It is made of the transition from opacity to transparency, the moment the fog cleared. Beyond that wall, farther back in time, the universe neutrinos. The first 380,000 years are hidden from us, at least from optical and radio observation, but they are not hidden from neutrinos. Neutrinos decoupled from the primordial plasma much earlier than photons did, roughly 1 second after the Big Bang, when the temperature dropped below about 10 billion degrees and the weak nuclear force could no longer keep neutrinos in thermal equilibrium with the rest of the plasma. These primordial neutrinos are still out there, filling all of space, even more ancient than the CMB photons. They carry information about the universe as it was just 1 second old. But detecting these cosmic neutrinos is extraordinarily difficult. They have been redshifted by the expansion of space to incredibly low energies, and neutrinos interact with matter so weakly that detecting even high-energy neutrinos is a major challenge. No one has yet detected the cosmic neutrino background directly, although its existence is inferred from the effects it has on the CMB and on Big Bang nucleosynthesis. It remains one of the great targets of experimental physics, a window into the first second of the universe's life. And beyond even the neutrinos, there may be gravitational waves from the first instance after the Big Bang, from inflation itself, ripples in space-time that carry information about the very birth of the universe. The primordial B modes we discussed earlier. The universe has multiple layers of ancient light, each one peeling back a little further toward the beginning, each one a little harder to detect than the last. Photons from 380,000 years, neutrinos from 1 second, gravitational waves from a trillionth of a second. Each layer is a new page in the universe's autobiography, and we are learning to read them one by one with instruments of increasing sensitivity and cleverness. The bed holds you, the night is deep, and the universe has written its story in layers of ancient radiation, each one a little fainter, a little older, a little closer to the beginning of everything. In and out. Let us think about the people who study the CMB, because their dedication is part of this story too. The CMB is studied by thousands of scientists around the world, physicists and astronomers and engineers and data analysts working with some of the most remarkable instruments ever built. Some of these instruments sit at the South Pole, where the air is extraordinarily cold and dry, which makes it ideal for detecting faint microwave radiation. The South Pole Telescope, a 10-meter dish enclosed in a giant shield to block ground-level radiation, has been observing the CMB since 2007, operating in temperatures of -60 degrees Celsius, staffed by small teams of researchers who spend months at the most isolated research station on Earth. Others sit high in the Atacama Desert of Chile, at altitudes above 5,000 meters, where the air is thin enough that some of the atmospheric water vapor that would otherwise absorb the CMB signal is below the telescope. The Atacama Cosmology Telescope operated there for years, along with other experiments with names like Polar Bear and Class and the Simons Observatory. And some are in space, orbiting the Sun at the L2 Lagrange point, 1.5 million kilometers from Earth, in the cold quiet of deep space, where the Earth and Moon and Sun are all on one side, and the the rest of the universe stretches out dark and clear on the other. These scientists spend years, sometimes decades, designing their instruments, testing them, deploying them, calibrating them, analyzing the data they collect, all in pursuit of ever more precise measurements of the oldest light in the universe. They are listeners, patient listeners, tuning their instruments to the faintest whisper from the most distant past, and extracting from that whisper the story of how everything began. The room is quiet around you, and somewhere on the planet, right now, someone is listening to the CMB, adjusting a detector, analyzing a spectrum, writing an equation on a whiteboard, or lying in a bunk at the South Pole after a long day of observations, as tired and human as you are, and perhaps just as ready for sleep. In and out. Let us now think about the relationship between the CMB and gravity, because gravity is the sculptor that turned the smooth, uniform universe of the CMB into the complex, structured universe we see today. At the time of recombination, the density fluctuations in the universe were incredibly small, about 1 part in 100,000. If the average density was like the surface of a perfectly still lake, the fluctuations were like ripples, 100,000th of a millimeter high. But gravity amplifies density fluctuations. A region that is slightly denser than its surroundings has slightly more gravitational pull, and that pull attracts matter from the surroundings, making the region denser still, which increases its gravitational pull further, which attracts even more matter. This is gravitational instability, the same process that caused the molecular cloud to collapse and form the sun, but operating on a much larger scale, taking density ripples 100,000th of a millimeter high on the cosmic lake and amplifying them over billions of years into mountains and valleys of matter, galaxies and voids, clusters and filaments. The process was slow, painstakingly slow. In the first few 100 million years, the fluctuations grew only modestly because the universe was still radiation-dominated and the pressure of photons resisted gravitational collapse on small scales. But after the photons decoupled at recombination, the brakes came off. Ordinary matter was free to fall into the gravitational wells that dark matter had already been deepening, and the growth of structure accelerated. The first dark matter halos formed, then the first stars within them, then the first small galaxies, which merged into larger galaxies, which gathered into groups and clusters, which connected into the vast cosmic web of filaments and voids that spans the observable universe today. All of this structure, every galaxy, every cluster, every void, every filament of the cosmic web can be traced back to the tiny temperature fluctuations in the CMB, the seeds planted by quantum fluctuations during inflation and nurtured by gravity over 13.8 billion years. The CMB is the baby picture, and the universe today is the adult. You can see the resemblance if you look carefully. The statistical pattern of the CMB fluctuations matches the statistical pattern of galaxy clustering. The same cosmic DNA expressed at different ages. You were once a baby too, and your baby picture would show a face that is recognizably yours. but simpler, smoother, not yet shaped by the experiences and growth that would come later. The CMB is the universe's baby picture, recognizable but not yet shaped by the 13.8 billion years of gravitational sculpting that produced the cosmos we see today. In and out, your muscles are soft, your jaw is loose, your hands are open, and the universe grew from a smooth, warm glow into the complex, beautiful structure it is today, shaped by gravity, shaped by time, shaped by the patient amplification of the tiniest quantum whispers. Let your own thoughts become simpler now, smoother, returning to a state of quiet uniformity, like the early universe before gravity began its sculpting, a smooth, warm glow of consciousness, without sharp edges, without structure, just warmth and light and rest. In and out. Let us now cycle back through the story one more time, slowly, gently, the way a lullaby returns to its chorus, letting the drifting listener catch what they missed, and letting the images wash over you like slow, warm waves. In the beginning, the universe was hot, hot beyond imagining, hot beyond description, a dense, brilliant fog of particles and radiation filling every point in space, with no edge, no center, no outside. And it was expanding, space itself stretching, carrying everything apart from everything else, like the surface of a balloon being inflated from within, every point moving away from every other point. As it expanded, it cooled. The temperature dropped from trillions of degrees in the first second to billions of degrees in the first few minutes, to millions of degrees over the following years, to thousands of degrees over the following centuries. And at each stage, as the temperature crossed certain thresholds, new things became possible. Quarks combined into protons and neutrons combined into atomic nuclei, and finally, at 3,000 degrees, 380,000 years after the beginning, electrons combined with nuclei to form the first complete atoms. And the fog cleared, and the light was free. That light has been traveling ever since, stretched by the expansion of space from visible light to microwaves, cooled from 3,000 degrees to 2.7 degrees, but still here, still everywhere, still carrying the pattern of density fluctuations that were the seeds of all the structure in the universe. And those density fluctuations, tiny ripples in the primordial plasma, were amplified by gravity over billions of years. Dark matter collected first, forming invisible halos. Then ordinary matter fell into those halos, condensing into clouds of gas, igniting into stars, gathering into galaxies. And in one particular galaxy, the Milky Way, in one particular spiral arm, a cloud of gas collapsed and formed a star we call the Sun, and around that star, a disk of gas and dust formed planets, and on one of those planets, life emerged and evolved, and eventually produced a being that could look up at the sky and detect the faint afterglow of its own origin. That being is you, lying in a bed, breathing slowly, surrounded by the oldest light in the universe, the light that carries the blueprint of everything. In and out. The blanket holds your warmth, the pillow holds your head, and the CMB holds the memory of the universe's birth. All three are holding something, keeping it safe, keeping it warm, keeping it close. Let us think about what the CMB tells us about the future. The CMB confirms that the universe is expanding, and the combined data from the CMB, from supernova observations, and from galaxy surveys tells us that the expansion is accelerating, driven by dark energy. This means that in the far future, galaxies will recede from each other faster and faster. The light from distant galaxies will be stretched beyond detection, and eventually, each galaxy group will be alone in an observable universe that appears to contain nothing else. The CMB itself will continue to cool, its photons stretched to ever longer wavelengths until they carry so little energy that they blend into the quantum noise of the vacuum and become undetectable. The oldest light in the universe will eventually fade away, not because it is destroyed, but because it is stretched so thin by the expansion of space that it becomes indistinguishable from nothing. If civilizations exist in the far future, trillions of years from now, they may have no way of knowing that the CMB ever existed. They would see only their own galaxy, surrounded by empty darkness, with no evidence that the universe was ever hot or dense or filled with ancient light. They would have no way of discovering the Big Bang, because the evidence would have been erased by the expansion of space. This makes our era special. We live at a time when the evidence of the universe's origin is still detectable, still measurable, still informative. We are privileged to see the CMB because future observers may not be able to. The night is deep. Your body is heavy with rest, and you are alive at the one moment in cosmic history when the oldest light is still visible, still carrying its information, still telling its story to anyone who will listen. In and out. The CMB also tells us something about the amount of ordinary matter in the universe, and the answer is surprisingly small. The ordinary matter that makes up everything you can see and touch, all the stars and planets and gas clouds and dust and people and animals and rocks and water, all of it together accounts for only about 5% of the total energy content of the universe. The rest is dark matter and dark energy, invisible, mysterious, detected only through their gravitational and cosmological effects. 5%. Everything you have ever known or experienced or imagined is part of the 5%. The 95% remainder is something we barely understand, something that does not emit light or interact with ordinary matter in any way we have been able to detect directly. And yet, the universe works, stars form, galaxies rotate, life exists, consciousness emerges, all of it powered by the 5%, supported by the 27% of dark matter, and carried along by the 68% of dark energy. You are made of the rarest stuff in the cosmos, and yet you are here thinking about the universe, wondering about its origin, resting in a warm bed on a planet that should not exist according to naive probability, but does exist beautifully, improbably, actually. In and let us spend a few more moments with the history of CMB observations, because each step in the story brought us closer to understanding where we come from. The prediction that the CMB should exist came decades before its discovery. In 1948, Ralph Alpha and Robert Herman, working with their mentor George Gamow, calculated that if the Big Bang theory was correct, the universe should be filled with a background of radiation at a temperature of about 5 degrees above absolute zero. Their prediction was remarkably close to the actual value of 2.725 degrees, considering the state of cosmological knowledge in the 1940s, but their work received little attention at the time. Cosmology was not yet a precision science, and the prediction was largely forgotten. It was not until the early 1960s that the idea was independently rediscovered by Robert Dicke and his colleagues at Princeton, who began building equipment to search for the radiation, only to be scooped by Penzias and Wilson's accidental discovery. After the initial detection, it took another 25 years before COBE could measure the CMB spectrum with sufficient precision to confirm that it was a perfect black body and to detect the tiny temperature fluctuations that encode the seeds of cosmic structure. Then WMAP refined the measurements by an order of magnitude, and Planck refined them by another order of magnitude. Each generation of instruments revealing finer details, sharper features, more precise numbers. The next generation of CMB experiments is already being designed and built. The CMB-S4 project, a collaboration of hundreds of scientists and institutions, will deploy 500,000 detectors at multiple observing sites in Chile and at the South Pole. It aims to map the CMB polarization with 10 times the sensitivity of Planck, finally reaching the level needed to detect or definitively rule out the primordial gravitational wave signal from inflation. And the Lightbird satellite, planned by the Japan Aerospace Exploration Agency, will observe the CMB polarization from space, complementing the ground-based measurements with observations that are free from atmospheric contamination. The story of the CMB is not finished. It is still being written by scientists who are pushing the limits of technology and ingenuity to extract every last bit of information from the oldest light in the universe. The room is quiet, your breathing is slow and steady, and the story of human understanding grows a little longer every year, a little deeper, a little more precise. Like the CMB itself, the story is patient. It does not rush. It unfolds at its own pace, one discovery at a time. In and out. There is a beautiful analogy that might help you understand why the CMB is so important to cosmologists. Imagine you are a detective and you arrive at a room where something important happened a long time ago. The room has been disturbed by subsequent events, furniture moved, walls repainted, new objects placed inside, but the ceiling has been left untouched, and on that ceiling, faintly, you can see the smoke stains from the original event, a pattern of marks that tells you exactly what happened in the room and when it happened. The CMB is the ceiling of the universe, the oldest undisturbed surface. The pattern imprinted on it 380,000 years after the Big Bang has been preserved across 13.8 cosmic evolution, while the rest of the universe has been dramatically rearranged by gravity and time. By reading the pattern on the ceiling, cosmologists can reconstruct the conditions in the room at the moment of the event: the temperature, the composition, the density, the pressure, the sound, the geometry. It is the most important piece of evidence in the cosmic crime scene, and we are extraordinarily fortunate to be able to see it. The pillow holds your head, the blanket holds your warmth, and the ceiling of the universe holds the story of creation, all three doing their quiet work of holding, preserving, keeping things safe. In and out. Let us think now about the sound of the CMB, not the pressure waves in the primordial plasma, but the actual sound you would hear if the CMB radiation were converted into audio frequencies. Scientists have done exactly this. They have taken the power spectrum of the CMB, the pattern of fluctuations at different scales, and shifted it into the range of human hearing. The result is a low rumbling tone like the hum of a distant engine or the resonance of a very large room, a deep bass note with overtones, the fundamental frequency and its harmonics corresponding to the acoustic peaks in the power spectrum. This is the sound of the universe at the age of 380,000 years, the frozen chord that was ringing through the primordial plasma when the fog cleared and the music stopped. It is the oldest sound in existence, although of course it is not really a sound. It is a pattern encoded in light, a visual representation of pressure waves that propagated through a medium that no longer exists in that form. But the poetry of it is undeniable. The universe sang once a single complex chord and then fell silent, and we have learned to hear that chord 13.8 billion years after it was played, by reading the pattern it left behind in the oldest light. The room is quiet now, so quiet that the universe's ancient chord would be loud by comparison, but you can hear it in your imagination, a deep, warm hum, the resonance of a cosmos that once vibrated with sound. Before the fog cleared and the silence of transparent space began. In and out, let us think about one more aspect of the CMB that is both strange and beautiful, its relationship with temperature and with the concept of absolute zero. Absolute zero. 0 degrees Kelvin minus 273.15 degrees Celsius is the lowest possible temperature, the point at which all thermal motion ceases, where atoms are as still as the laws of quantum mechanics allow them to be. No object in the universe has ever been observed at absolute zero. And the third law of thermodynamics tells us that no object can ever actually reach it. You can get very close, incredibly close, but you can never quite get there. The CMB sets a floor for the temperature of the universe, 2.725 degrees above absolute zero. Any object left alone in space, far from any star or heat source, will eventually cool to this temperature and no further, because the CMB photons arriving from every direction will keep it warm, delivering a tiny but persistent trickle of energy. It is as though the universe has a minimum setting, a baseline warmth below which nothing can fall, set by the afterglow of its own creation. In laboratories on Earth, scientists routinely cool things to temperatures far below the CMB, Using laser cooling and magnetic traps and evaporative cooling techniques, they have brought clouds of atoms down to billionths of a degree above absolute zero, thousands of times colder than the coldest spot in the universe. But they can only do this by actively pumping heat away, fighting against the relentless flow of thermal energy from the environment, using enormous amounts of energy and ingenuity to create tiny pockets of extraordinary cold that last for fractions of a second before warming up again. In space, without active cooling, the CMB is the limit. 2.725 degrees Kelvin, the temperature of the cosmos itself. Your bed is much warmer than the CMB, roughly 310 degrees Kelvin, the temperature of a living human body, more than 100 times warmer than empty space. You are a tiny, hot island in a cold universe, a concentration of warmth in an ocean of chill. But the CMB is warmer than absolute zero, which means that even the emptiest voids of space are not truly cold. They carry a memory of warmth, a remnant of the fire that began everything. The universe was born hot, and it has never fully cooled. Not yet, not for a very, very long time to come. In and out. Let us think about one of the most poetic aspects of the CMB, the fact that it connects us to the very beginning of time. You cannot visit the site of the Big Bang. There is no such site. The Big Bang did not happen at a particular location in space. It happened everywhere, at every point in the universe simultaneously. Because the Big Bang was not an explosion in space, it was the creation of space itself. You cannot travel back in time to witness the Big Bang. You cannot build a telescope powerful enough to see it directly, because before recombination, the universe was opaque and no image can be formed. But you can detect the CMB, and the CMB is the closest thing we have to a physical connection with the Big Bang. It is the afterglow, the residual warmth, the echo, the cosmic equivalent of the warmth that remains in a room after the fire has gone out. When scientists measure the CMB, they are touching the edge of the Big Bang. They are reaching across 13.8 billion years of time and touching the moment when the universe first became transparent. The moment when light was born into freedom. And that light is touching you right now, passing through your body at the speed of light. Ancient photons that were last scattered by electrons 380,000 years after the Big Bang. Photons that have been traveling through an expanding universe for longer than the Earth has existed, longer than the sun has burned, longer than the Milky Way has been turning. You are in physical contact with the afterglow of creation. It is as close to touching the Big Bang as any material object can ever be. The room is dark and warm. Your body is still and quiet, and the oldest light in existence is passing through you, whispering its ancient story in wavelengths you cannot hear, but that carry more information about the origin of the universe than any other signal in nature. In and out. Let us rest now with one more thought about the CMB, perhaps the most personal thought of all. The CMB is the same everywhere in the universe. Every intelligent dimensions, the same baby picture of the cosmos. If there are other civilizations out there, other beings who have developed radio telescopes and satellite observatories and the mathematics to analyze what they find, they are seeing the same CMB that we see. They are drawing the same conclusions about the age and composition and geometry of the universe. They are discovering the same baryon acoustic oscillations, the same power spectrum peaks, the same evidence for inflation and dark matter and dark energy. The CMB is a universal heritage shared by every conscious being in the cosmos. It is the one thing that every civilization in the universe has in common, the one signal that connects us all, regardless of where we are, or what we look like, or what language we speak. You are part of a cosmic community of observers, all looking at the same ancient light, all reading the same cosmic autobiography, all connected by the afterglow of a beginning we all share. That thought can be a comfort tonight. You are not alone, not in the deepest cosmic sense. The universe is vast and old, and perhaps full of beings who are doing exactly what you are doing right now, lying in their equivalent of beds, looking at their equivalent of skies, and wondering about the same ancient light. In and out, let us drift now through the story one final time, very slowly, very gently, letting each idea arrive like a single note in a quiet melody. A hot, dense universe, expanding, cooling, filled with a fog of plasma and light. 380,000 years of cooling, the temperature dropping from billions of degrees to thousands, the universe stretching and thinning, the fog slowly becoming less opaque. And then, at 3,000 degrees, the electrons find their homes, settling into orbit around nuclei, forming atoms for the first time, and the fog clears, and the light is free. The photons fly outward in every direction, carrying with them the imprint of the primordial sound waves, the pattern of hot and cold spots that would one day become galaxies and voids and the great cosmic web. They fly for 13.8 billion years, stretched by the expansion of space, their wavelengths growing longer, their temperature cooling from 3,000 degrees to 2.7 degrees. Visible light becoming microwaves, a brilliant glow fading to an invisible whisper. And then, one night in 1964, two men in New Jersey hear a hiss in their antenna that they cannot explain, and the oldest light in the universe is discovered by accident. COBE measures its spectrum and finds it perfect, a flawless black body curve, the most thermally balanced system in nature. COBE finds the ripples, tiny variations in temperature, 1 part in 100,000, the seeds of everything. WMAP sharpens the picture, revealing the acoustic peaks, the frozen harmonics of the cosmic chord. Planck perfects the image, measuring the composition of the universe, its age, its geometry, its fate. And tonight you rest, bathed in the afterglow of the Big Bang, surrounded by photons that have been traveling since before stars existed, ancient light that asks nothing of you, that touches you as gently as a whisper, that carries the story of everything and tells it to anyone who will listen. In and out. Your body is very quiet now, very still. The muscles of your face have softened. Your hands are open and relaxed. Your breathing has found its own slow rhythm, without guidance, without effort, like the expansion of the universe, steady and unhurried. The CMB is a kind of lullaby, a cosmic lullaby, a single long note that has been playing for 13.8 billion years. Too quiet for your ears, too low for your instruments, without extraordinary amplification, but always there, always humming, always surrounding you. It is the universe's way of saying, I was here before you, and I will be here after you, and while you are here, I will hold you in my ancient light, the way a parent holds a sleeping child, gently, quietly, with nothing to prove and nothing to ask for. Only the simple act of holding. The universe holds you in its afterglow. The oldest light in existence wraps around your body and passes through you and continues on its way, having kept you company for this one small night in its 13.8 billion year journey. It does not know you are here. It has no awareness, no mind, no intention, but it is here, and you are here. And for this brief moment, the oldest light and the youngest thought share the same space. In and out. In and out. Let us think about what happens to the CMB photons that pass through your body tonight. Most of them will continue straight through, barely interacting with the atoms you are made of. They will pass through the walls of your room, through the atmosphere of the Earth, and back out into space, continuing their journey across the expanding universe. A tiny fraction of them will be absorbed by molecules in the air or in your body, their energy converted into a slight warming, an immeasurably small increase in the temperature of whatever absorbed them. The energy of a photon from the Big Bang deposited into the atoms of a living human and converted into the thermal motion of molecules. In that moment of absorption, the photon's 13.8 billion year journey ends. Its energy becomes part of you, blended with the chemical energy of your food, the electrical energy of your neurons, the thermal energy of your body heat. A tiny parcel of the Big Bang becoming part of a sleeping person for a fraction of a second before being re-radiated as infrared photons from your skin, heading back out into the universe in a new form, at a new wavelength, carrying new information about the temperature and composition of a human body in the 21st century. The universe recycles its energy endlessly. The photon from the Big Bang becomes the warmth of your skin, becomes a new photon heading out into space, energy changing form but never being destroyed, passing through state after state, era after era, always conserved, always present, always moving. You are a brief stop on a very long journey, a moment of consciousness in the middle of an endless chain of energy transformations that stretches from the Big Bang to the heat death of the universe. And tonight, in this moment, the chain passes through you, and you can rest in the knowledge that you are part of something continuous and ancient and beautiful. In and out. There is one more connection worth making before the story is complete, a connection between the CMB and the deep future we explored in other journeys. The cosmic microwave background is cooling. It has been cooling since the moment it was born, its temperature dropping as the universe expands from 3,000 degrees at recombination to 2.7 degrees today. In the far future, as the universe continues to expand, the CMB will cool further. In 1 billion years, it will be slightly below 2 degrees. In 10 billion years, it will be around 1 degree. And in the very distant future, trillions and trillions of years from now, it will approach absolute zero, but never quite reach it. The oldest light in the universe is slowly fading away, not because it is being destroyed, but because it is being stretched so thin by the expansion of space that its energy becomes almost nothing. One day, in the incomprehensibly distant future, the last CMB photon to interact with anything will deposit its final quantum of energy into the last object capable of absorbing it, and the afterglow of the Big Bang will pass into the background quantum noise, indistinguishable from the zero-point fluctuations of empty space. The universe will have forgotten its own birth. But that is so far in the future that the number of years between now and then makes the current age of the universe look like a rounding error. Tonight, the CMB is still bright enough to measure, still warm enough to detect, still rich enough in information to fill scientific journals and inspire awe. It is in the prime of its observable life. If 13.8 billion years can be called prime. And you are here to witness it. You are alive at a time when the oldest light is still telling its story, when the cosmic ceiling still shows its smoke stains, when the baby picture of the universe is still on display for anyone with the right instruments to see. That is a privilege, a quiet and unasked for privilege. The universe did not create you so that you could observe the CMB, but you can observe it nonetheless, and that is remarkable. In and out. Let us rest now with one final image. Imagine yourself floating in space, far from any star, far from any galaxy, in the vast cold dark between the clusters of the cosmic web. There is nothing around you for millions of light years. No light, no warmth, no sound, only the infinite dark. And then, gradually, your instruments become sensitive enough to detect it, a faint glow coming from every direction equally, warm and uniform and ancient, the afterglow of the Big Bang, the cosmic microwave background. It is not bright enough to see with your eyes, but it is there. You can feel it with the right detectors. You can measure its temperature 2.725 degrees above absolute zero. You can map its pattern, the tiny fluctuations that encode the seeds of all structure. And in that glow, in that ancient faint warmth, you are not alone. You are surrounded by the afterglow of the beginning of everything, held in the embrace of the oldest light, connected to the Big Bang itself by a chain of photons that has never been broken. You are bathed in the light of creation, and that light has been there, waiting for you, since before the earth existed, since before the sun burned, since before the Milky Way formed, since the very first moment the universe became transparent and the cosmos drew its first clear breath. The bed holds you, the room is dark, The night is deep, and the oldest light in the universe shines on. In and out. In and out. In and out. Rest now in the afterglow, in the ancient warmth, in the quiet. Let us linger in the quiet now, not adding new ideas, but letting the ones already spoken settle around you like snow falling in a windless night. The cosmic microwave background is the afterglow of the Big Bang, the oldest light in the universe, released when the cosmos was 380,000 years old and the primordial fog cleared for the first time. It has a temperature of 2.725 degrees above absolute zero, cooled from 3,000 degrees by 13.8 billion years of expansion. It carries within its pattern the seeds of every galaxy, every star, every planet, every person who has ever lived or ever will live, encoded in tiny temperature variations 100,000th of a degree above and below the average. It was discovered by accident in 1964 by two scientists annoyed by a hiss they could not eliminate from their antenna. It has been mapped with extraordinary precision by COBE, WMAP, and Planck, revealing the age, composition, and geometry of the universe. It carries the frozen harmonics of sound waves that rang through the primordial plasma, a cosmic chord that played for 380,000 years and then fell silent. And it is here, right now, passing through you as it passes through everything ancient and faint and patient and everywhere. These are the facts, and they are beautiful, and they are enough. In and out. Let your breathing become very slow now, so slow that you can barely feel it. Each inhale, a long, gentle drawing in of air. Each exhale, a long, gentle release, like the universe itself, expanding and resting, expanding and resting. A cosmic respiration that has been going on for 13.8 billion years. The room is dark, the house is quiet, the street outside is sleeping, half the planet is turned away from the sun, wrapped in the shadow of the earth, bathed in starlight and moonlight and the invisible ancient glow of the CMB. You are one of billions of people resting right now on a planet orbiting a star in a galaxy of hundreds of billions of stars in a universe of trillions of galaxies, all of it illuminated by the oldest light there is, all of it carrying the pattern of the primordial fluctuations, all of it connected by the afterglow of a beginning that everything shares. The CMB does not care whether you are awake or asleep. It does not care whether you understand it or not. It simply is. It simply shines in its own cold, quiet way, the most democratic light in the universe, reaching everything equally, touching everything equally, asking nothing in return. Let it shine on you tonight. Let it pass through you. Let it carry its ancient story past your sleeping body and on into the expanding dark. You do not need to hold it. You do not need to understand it. You only need to rest. In and out. The universe began as a single point of unimaginable energy and expanded into everything you see, everything you know, everything you are. The afterglow of that beginning is still here, still visible, still measurable, still telling its story to anyone who points an instrument at the sky. And you are part of that story, a chapter near the middle, written in atoms that were forged in stars that condensed from gas that was shaped by the fluctuations encoded in the afterglow. You are a consequence of the CMB in a very real sense, the pattern of hot and cold spots that decorate the oldest light in the universe determined where galaxies would form and where stars would burn and where planets would coalesce and where life would arise and where you would be tonight in this room, in this bed, breathing this air, thinking these thoughts. If the fluctuations had been slightly different, the Milky Way might have formed somewhere else, or not at all. The sun might have formed in a different part of the galaxy, or a different molecular cloud. The Earth might have been a little closer or a little farther from its star, and you might not be here. But the fluctuations were exactly what they were, and here you are, resting, listening, drifting towards sleep, a brief and beautiful consequence of the pattern encoded in the oldest light. In and out. In and out. Sleep now, the way the early universe rested after the fog cleared quietly, transparently, with nothing left to scatter and nothing left to block. Just clear open space stretching in every direction, and light, ancient light, traveling freely for the first time. Sleep the way the photons travel, without effort, without resistance, at the speed of rest, following the curves of space-time wherever they lead. Sleep the way the CMB fills the universe, uniformly, patiently, without preference or purpose, simply being present, everywhere, always. And dream, if you dream at all, of a warm fog lifting and light streaming outward in every direction, and a universe that is young and smooth and full of potential, waiting to become everything it will one day be. The stars will be there when you wake, the sun will rise, the sky will brighten, and the CMB will still be here, faint and ancient and faithful, the afterglow of the beginning, the oldest light, your silent companion through every night of your life. In and out. In and out. In and out. And now the stars begin to dim behind your thoughts. You are a part of this cosmos. The carbon in your body was forged in the hearts of ancient stars. I hope you sleep well and dream softly. Good night. Let us explore one more idea before the night deepens further, an idea about the horizon of the observable universe and what the CMB teaches us about how much of reality we can see. The observable universe has a radius of about 46.5 billion light-years. This may seem strange, since the universe is only 13.8 billion years old. How can the radius be larger than the distance light could have traveled in 13.8 billion years? The answer is the expansion of space. The photons of the CMB that are reaching us now were emitted from a region that was about 42 million light-years away at the time of emission, 380,000 years after the Big Bang. But since then, the space between us and that region has been expanding, and the actual distance to that region today is about 46.5 billion light-years. The photon did not travel 46.5 billion light light years, it traveled through expanding space, riding the stretching fabric of the universe like a message on a conveyor belt that is getting longer even as the message moves forward. The surface of last scattering, the wall of the CMB, is the edge of our observable universe. Beyond it, the universe continues, probably indefinitely, but we cannot see what is there because the light from those regions has not yet had time to reach us. Or more precisely, the universe was opaque before the CMB was released, so even if light from those earlier eras could reach us, we would not be able to see through the fog. The observable universe is like a spotlight, illuminating a sphere of space around us, showing us everything within reach of the oldest light and leaving everything beyond in darkness, not because it does not exist, but because its messengers have not yet arrived. How much universe lies beyond the observable boundary, no one knows. Some theoretical models suggest it might be unimaginably vast, perhaps infinite. Perhaps the universe extends forever in every direction, with more galaxies and more CMB photons and more structure, repeating the same patterns with endless variation. Or perhaps it curves back on itself like the surface of an enormous sphere, finite but without edges, and if you could travel far enough in one direction, you would eventually arrive back where you started. The CMB tells us that the universe is flat, or very close to flat, which is consistent with an infinite universe, but does not prove it. Flatness is also consistent with an extremely large but finite universe that curves so gently we cannot detect the curvature. We do not know the answer, and perhaps we never will. The observable universe may be all we can ever study, a small, bright bubble in something much larger and forever unknowable. There is a peacefulness in not knowing, a comfort in uncertainty. Not everything needs to be resolved or explained or pinned down. Some questions are companions rather than problems. They walk with us through the night, keeping us company, asking nothing, demanding nothing, simply being. In and out. Let us think for a moment about what you are doing right now in cosmic terms. You are lying on the surface of a small rocky planet, the third from an ordinary yellow star in an ordinary spiral arm of an ordinary galaxy. You are made of atoms that were forged in the cores of stars, that lived and died before the sun was born. Atoms that were present in the molecular cloud that collapsed to form the solar system 4.6 billion years ago. Above you, through the roof and through the atmosphere, the night sky stretches upward, filled with stars and galaxies and dark matter and dark energy, all of it bathed in the faint invisible glow of the cosmic microwave background. Your body is warm, roughly 310 degrees Kelvin, one of the warmest objects in this part of the galaxy. Most of the matter in the Milky Way is either very hot in the cores of stars or very cold in the dark of space. Your body sits in a narrow, comfortable band of temperature between these extremes, warm enough for water to be liquid, warm enough for chemistry to operate, warm enough for life. The CMB passes through you at 2.7 degrees above absolute zero. The sunlight that warmed you today was 5,778 degrees at its source. The air you breathe is about 295 degrees. Your body maintains itself at 310 degrees through the burning of chemical fuel. You're a small, warm island in a cold universe, kept alive by the energy of a star, on a planet kept warm by an atmosphere, in a cosmos kept above absolute zero by the afterglow of the Big Bang. Layers of warmth, each one nested inside the next, like blankets piled on a bed. The Big Bang's afterglow, the sun's light, the Earth's atmosphere, your blanket, your body heat, each one holding a little more warmth than the layer above, each one keeping you a little more comfortable. In and out. The night deepens, your thoughts grow thinner, lighter, fewer, like the thinning of the primordial fog before recombination, each thought scattering a little less frequently, each one traveling a little further before fading. Soon your thoughts will decouple from consciousness entirely, the way the photons decoupled from the plasma, and they will fly free into the space of dreams, carrying whatever patterns they carry, wherever they choose to go. You cannot control where your dreams will take you, any more than the CMB photons can control where the expansion of space carries them. You can only release them, let them fly, and trust that wherever they go, you will be safe. The bed holds you, the room holds you, the planet holds you, the sun holds you in its orbit, the galaxy holds you in its spiral arm, and the afterglow of the Big Bang holds everything, everywhere, all at once, in its ancient, gentle embrace. In and out. In and out. In and out. Good night.